Hello there and welcome back to this video series on control systems. In the past couple of videos, we have seen how principle of argument in complex variable theory led us to Nyquist criterion. We have shown what we mean by Nyquist path, the big semicircle and small semicircle and the kind of stuff, and what is Nyquist plot. We have seen what is Nyquist criterion as an application of principle of argument in the theory of complex variables. We will try to use the previous video material in the previous video to draw a Nyquist plot for a simple transfer function and present it as an example, based on which you will perhaps be able to draw the Nyquist plot for simple transfer functions and apply Nyquist criterion for determining the stability of such systems. Let us dive into the video. We will now lay down clearly the steps involved in applying the Nyquist criterion as given here. So we'll consider the Nyquist path, which is this one circle or two circles as shown here. Let us go back again and do it. It is this one big circle going on as shown here, or the two circles, one very big circle, one very small circle. The small circle is used when we want to avoid a pole at the origin. Then step 2 would be to count the number of poles that are lying in this path, the number of points lying here or number of points lying here, as the case may be. This path is used when a pole or zero exists at the origin, specifically when a pole exists at the origin. You count the number of poles that are lying in the Nyquist path. Let this number be t. Then draw the Nyquist plot for the fs, that is on the fs plane. Count how many times this encircles minus 1 plus j0. Let that number be n. Compute z is equal to n plus p. Z should be 0 for stability. Let us try to apply this to an example problem and see. Let us consider an example transfer function 10 over s into 0.1s plus 1 and see how we can ascertain the stability of using Nyquist criterion. There is a pole at origin. To avoid the pole at origin, we consider the Nyquist path with a small semicircle, because we don't want to hit this pole at origin. Okay, we want the fs to behave well at each point on the path. We don't want this 0 coming in here. Then you have 10 over 0, which we don't want. Okay, so clearly we see that there are two poles here. One is s is equal to 0, one is s is equal to minus 10. None of these poles are lying within this graph, so we see that p is equal to 0. Now, corresponding to each point on this plot, we will try to compute what is fs, that is fs1, fs2 and so on. Okay, let us show that. For convenience, we say that this path consists of 4 segments. This is segment 1, C1, going from here to infinity, all the way up to infinity, starting from here all the way up to infinity. Segment 2 is this big semicircle. Segment 3 is this segment on the negative imaginary axis, and segment 4 is this small semicircle. You may note one thing: this C1 and C3, C1 here on the positive axis and C3 on the negative axis, are mirror images of one another. So when you plot fs, the plot corresponding to C1 is mirror image of plot corresponding to C3 and so on. So we'll begin with this segment C1. C1 is the segment of positive imaginary axis extending from the tip of the small semicircle all the way up to infinity, because this circle, this big circle's radius tends to infinity. Okay, we'll substitute s is equal to j omega, because all the points here will not have any real part, they have only imaginary part. So s is equal to j omega, and you have this transfer function. You multiply both numerator and denominator by the complex conjugate and simplify, you get this f of j omega. You can very closely see that when omega tends to 0, because our range of values of omega will go from 0 all the way up to infinity. When omega tends to 0, this part is 0, so you have this whole thing becomes minus 1. That is the reason why you have an asymptote drawn at minus 1. And this, when omega tends to 0, this term becomes very big, extremely big. That is what we note here. When omega tends to 0, f of j omega tends to infinity, and angle of f of j omega tends to minus 90. You can see if this is the line, the angle this line makes is minus 90 degrees. And also when you see when omega tends to infinity, when omega is very big, okay, this magnitude tends to 0, because something big is there in the denominator. And angle minus 1 and this whole big thing tending to 0. So the vector is from here to minus 1, which is minus 180 degrees. So when omega tends to 0, magnitude is infinity, phase angle is minus 90, so it begins somewhere here. When omega tends to infinity, it's very close to origin, very close to origin. We cannot show it so close. If you show it very close, you cannot see that there is a gap. Okay? And angle is minus 180. So this is the Nyquist plot corresponding to segment C1. It may be confusing, but if you solve a couple of problems, I'm sure it adds a lot of clarity. It did to me. I solved several problems and it is clear to me. Now if you do it, it will be clear to you too. So C1 is over. Let us come to the segment C2, which is a very big semicircle of Re power j theta form. R tends to infinity and theta varies from plus 90 to minus 90. That you can see very clearly here. Theta is plus 90 here, it came all the way to minus 90 there. Okay. So this is the expression you have when you substitute s is equal to r e to the power of j theta. This r tends to infinity, so this term is very big compared to 1. So just neglect this term and you have 10 by tau r square, tau r, one more r, e power j theta plus j theta, j 2 theta. So you represent this by 10 by tau r square at an angle of minus 2 theta. Okay. So when theta varies from 90 to minus 90, minus 2 theta varies from minus 180 to plus 180. Okay. That is how you have from minus 180 very close to imaginary axis and plus 180 again close to imaginary axis on the close to real axis. Sorry, this is close to real axis here, that is at minus 180 degrees, and again coming close to real axis from the other side. So this is the path corresponding to C2. Then we say that path corresponding to C3 is mirror image of this as shown here. Okay. The final last segment is small semicircle C4. We say s is equal to r e power j theta, where r tends to 0 and theta varies from minus 90 to plus 90 degrees. Why this is so? Look at the Nyquist path and find out why it is from minus 90 to plus 90. So when you substitute s is equal to r e power j theta, you have this term coming in. This is very small, extremely small as compared to 1. So neglect that. If you neglect that, you have 10 by r at an angle of minus theta. When theta varies from minus 90 to plus 90, minus theta varies from plus 90 to minus 90. You need to carefully write that down and think it through to make sense. If you just listen and let it go, you may not get the full grasp of it. So theta varies from minus 90 to plus 90. Put a negative. This becomes 90 and this becomes minus 90. So you have this big circle starting at somewhere near 90 degrees, somewhere on the imaginary axis, coming all the way back and closing the loop. Now you count the number of encirclements of this minus 1 J0 point. You draw a line from minus 1 J0. See, there is one going in clockwise direction, one arrow going in counterclockwise direction. So the number of encirclements n is 0, p is 0. So z is equal to n plus p is equal to 0. So the system is stable. If we look at it now, it looks as though we are doing too much of computation for a simple problem, a simple case of detecting stability. But Nyquist criterion is kind of powerful. It leads us to body plot and polar plot later. And if we apply such powerful tool to a simple problem, it appears complicated to us. It is like dropping a hydrogen bomb on a sparrow. You don't need a hydrogen bomb. Similarly, you don't need Nyquist criterion to find the stability of a simple first order or second order system. You can do that by Routh's criterion and root locus plot if the need arises. But in any case, this is the concept. You get the complete Nyquist pair on FS plane, count encirclements, and z, compute z. This z better be 0 for stability. In fact, if the transfer function were to be given as k over s into 1 plus tau s instead of 10 and 0.1, okay, we can infer from Nyquist criterion that the closed loop system is stable for all k greater than 0 and for all tau greater than 0. I would leave that as an exercise. So to summarize, we have seen Nyquist criterion with the help of an example, and it is a bit tricky to draw the Nyquist plot. So a lot of practice is needed. Unless you practice, you may not get the grasp of it. That's all I think we have for now. Have a great day.